Hi guys, sorry I couldn't be in class today. I do want to record this video though to give you some notes about the new unit that we're starting, which is going to be forces and motion, also called dynamics, also called Newton's laws, if you've heard of those. And the reason we're learning this in physics is because Newton's laws help us to understand the relationship between force and motion. In other words, like, why do objects move the way they do? How do we get an object to move or an object to stop moving? And the answer is force. So this is a very important concept in careers like engineering, like when you're building bridges and you have to think about forces, or you're building buildings and you have to think about forces and balancing those out. If you're building a machine, is it strong enough to handle the actual job that it's going to do? Is it capable of doing what you want it to do? Anything like that. And even like simple things like everyday life, like when you're driving, use a whole lot of physics during driving, use a whole lot of physics during sports if you play sports, and things like that. So we're going to start right off with Newton's first law of motion. Newton's first law of motion states that an object in motion stays in motion with the same speed and direction it was traveling in, unless it's acted upon by a net force or an unbalanced force. And similarly, an object at rest stays at rest unless acted upon by a net external force. Okay, so this is a really long way of saying that there's this thing called inertia. So however an object happens to be moving at the moment that you're studying it, the object is going to keep moving in that same way, whether it's staying still, rolling forwards, rolling backwards, uphill, downhill, whatever it may be, until you add another force to it in order to change its motion. So this law, Newton's first law, is also called the law of inertia. Alright, so just to write it out for you in a slightly different way, inertia is an object's tendency to maintain its state of motion. Okay, so if you're wondering how inertia came to be, like why do objects have a tendency to maintain their state of motion, the answer to that is simply because all objects have mass. Okay, so you probably learned in chemistry that mass is the amount of matter in an object. So how massive an object is depends on how many particles are inside of it, making it up, what type of particles there are, how dense the particles are, things like that. And so things with more mass or more particles are going to be better at maintaining their state of motion, or in other words, they are going to be more resistant to a change in motion. So more massive objects are more resistant to changing their motion. So what does that translate to in this unit? That translates to you're going to need more force in order to move or change the motion of an object that is very massive. Just to clarify real quick, we'll talk about this more later, but mass, when we're talking about inertia, mass is not the same thing as weight. So keep that in mind. Weight is actually a force in and of itself, while mass is the actual chemical makeup of the particles. If you would like some everyday examples of inertia, the best one that I can think of is when you're driving in a car. Say someone else is driving, you're sitting in a car, and the person hits the brakes, the person who's driving. The car slows down, and you're going to feel yourself move forwards in your seat when it does that. And the reason is because the brakes are acting on the car in order to slow it down. So the brakes act as a force on the car to slow it down. The brakes are not acting directly on you. There's no extra external force being put on you when the driver hits the brakes. So therefore, you want to keep moving in the direction the car was moving before, in the direction you were moving in before. And that's why your seatbelt is very important, because without it, if you slam on the brakes really hard, you would just keep going and fly right through the windshield. Okay, the seatbelt provides that force that is needed to keep you from moving forward that far into the windshield. Another example is if you are swinging something around, like in a circle, like this, and I let go of this at some point, it goes straight. It doesn't keep going in a circle. And that's because at the point that I released it, it was facing that way. So in that moment, the direction of my lanyard was actually this way. But it was going in a circle, so the direction of its motion was changing every second. But at the moment that I released it, it was going that way. So when I let go, I released the tension force that was causing the circular motion. It kept going in a straight line in the direction it was going in that one moment. Okay, so now that we know what inertia is, what Newton's first law kind of means, I want to go over briefly the types of forces that you're going to encounter in this unit, and we'll go over them more in depth later. Okay, so here are some examples of forces. Friction. Applied force, which is like a person pushing. Like this, for example. Don't mind my drawing. So this person pushing on the box this way is your applied force. You could have the tension from a rope. So if this is your rope, you might be pulling the box that way. There's spring force, which is exactly what it sounds like, the force from a spring. So springs, you know, have their like natural state, and if you compress a spring, it's gonna wanna expand back to its natural state, and if you stretch a spring, it's gonna want to compress back to its natural state. So if you attach some object to a spring that is compressed, your spring is going to want to decompress, and it's going to push the box that way. Similarly, if you had a very stretched out spring with an object attached, your stretched out spring is going to want to compress, so it would pull the object that way. Again, this is just a brief overview. We'll go more in depth with these later. There is the force of gravity, which you are all very familiar with now. And then there is this thing called the normal force. Okay, so a normal force is a contact force from a surface that basically just prevents the object from falling through a surface. Okay, so for an example of a normal force, let's say you have a table here. There's your table. And on your table, you have yet another box. The normal force acting on this box is actually going to push up on the box from the table. So it's basically just saying like the table is strong enough to hold up the box, but in order to do that, it has to exert a force on the box because gravity is also acting on this box and pushing it down. So some other force has to counteract that gravity in order to hold the box in place on top of the table. So this is your normal force, this bottom arrow here. Okay. A very important thing that we're going to have to be able to do in the forces unit is find the net force acting on an object. So let's talk about what net force means. It was in the definition of Newton's first law. I didn't really tell you what it meant. We're going to go over it now. The net force is just the sum of all the forces acting on an object. Okay, and if you don't know this word from math, it just means addition. You're adding up all the forces that are acting on an object. Also important here is that force is a vector. Meaning, in this unit, again, you're going to have to identify a reference frame which direction is positive, which direction is negative. And when you add your forces, you need to have the correct sign, either positive or negative, on your value for force. Very similar to last unit. Also, here, the net force is the sum or addition of all force vectors acting on an object. So you have to remember in this unit that you're going to be focusing on one object. So it's not going to matter how many forces exist in the scenario that I give you. All you need to know are the forces acting on the one object that I'm asking you about in the problem. And to help you out with this, we draw these things called free body diagrams. And I'm going to erase this so I have plenty of room to talk about free body diagrams. So free body diagrams, also known as FBDs for short. What a free body diagram is it is basically just a diagram of your one object that you're going to be focusing on in a problem. And specifically, it's a diagram of this one object with all irrelevant information removed. Okay, so what do I mean by this? What I mean is, for example, you always show your object that you're focusing on as a square. I don't care if it's a ball, I don't care if it's a car, you show it as a square. Also, it shows only the forces acting on the object. And you're probably like, well, duh, it shows the forces acting on the object. That's the object I'm focused on. But sometimes the scenario will have two objects, for example. Like think about a car crashing into something, for example. If the car crashes into a telephone pole, the car is going to exert a force onto the telephone pole. But if the problem is asking you about the car, you don't care if there was a force exerted by the car on the telephone pole. All you care about is what forces are acting on the car, not what forces are exerted by the car. Only which forces are acting on the car. And that will get easier with practice. I'll just add that here. Also, importantly, you need to show your forces pointing in the correct direction. which again, we need a reference frame for. And it shows all the forces pointing away from the object or away from the square or the box. So this one might be a little confusing. All forces are drawn pointing away from the object. So if we use the example that I drew before with the table, and I said there was a box on the table, before I drew it this way. I said this is your normal force. Alright, normal force, force of gravity, and I drew it this way. But when you draw a free body diagram, here's the same box, except you're going to draw all the arrows going away from the object. So instead of drawing it like this, I'm going to draw it like this. So you can see here, the reference frame is the same. So let's say I'm going to make this positive and this negative. Same over here. My gravity arrow is still pointing downwards in the negative direction in both pictures. And the normal force arrow is pointing upwards in the positive direction in both pictures. The difference is that in the FBD, you make sure all your arrows point away from the object. Okay, and the last thing that you want to do is make sure that you label all the forces in your free body diagram. Meaning, I labeled this one the force of gravity, and I labeled this one the normal force. That's what I mean by label your forces. Okay. So I want to give you a couple examples of free body diagrams and how you can use them to find the net force or the sum of all the forces like we were talking about before. Okay, so for example, let's say I have a shopping cart and Bob and Sally are pushing the shopping cart. Okay, and they're pushing it together, so they're both pushing the same shopping cart. pushes the cart with 8 newtons of force. Newtons, capital N, is the unit for force. Bob pushes with 8 newtons and Sally pushes with 5 newtons of force in the same direction as Bob. So let's say part A is just draw the free body diagram of the shopping cart. First thing you're going to do is draw a square. Those of you who are not good at arts are going to love this unit. Everything is a square. Alright, so there's the shopping cart. The next thing you're going to do is set your reference frame. If you don't want to write it every time, like last unit, it was really helpful to label which direction was negative and which direction was positive. When we draw the free body diagrams, the general convention is just positive is upwards, negative is downwards, negative is left, and positive is right, just like we've been doing. So you don't have to, I'm not going to require you to label it like this every time you reference frame. Just know that it's like that. So Bob pushes with 8 newtons. It doesn't say if it's in the positive or negative direction. And in this unit, it doesn't matter. You can choose whichever direction Bob is pushing in. So we're just going to choose positive. Okay, the force of Bob, or the force Bob exerts on this shopping cart is 8 newtons this way. Sally pushes with 5 newtons of force in the same direction. So Sally's also going to be over here. This is the force from Sally equals 5 newtons. And the reason it doesn't matter if you say they're pushing in the positive or negative direction is just because the problem is just centered around this one object. So like if I said Bob and Sally were pushing in opposite directions, you would make one of them push in the positive direction and one of them push in the negative direction. But it doesn't matter so much which direction. As long as when you like circle your answer at the end, you specify the direction there. Okay, so here is our free body diagram. That's it. Right here. And as we go along, you'll see that there are more than these two forces acting on the shopping cart, but we haven't gotten there yet. We're just practicing free body diagrams. So we're just going to keep it like this for this example. Let's say part B asks you to find the net force acting on the shopping cart. Remember, in our free body diagram, we only draw the forces acting on the cart. Okay, so we use this to answer that question. The net force, you can write it 2 ways. I usually write it like this, because this little symbol means the sum of all the forces, aka the net force. Or you can write it as F sub net if you like it better that way. So find the net force. What did we say the net force meant? We said it means you add up all the forces acting on your object, making sure you keep the correct directions in mind. So here, Bob and Sally are both pushing in the positive direction, so all you have to do is add up 8 plus 5, which is going to give you 13, I believe, 13 newtons. That's the net force acting on the shopping cart. If Bob and Sally were pushing in opposite directions, let's do that problem now. Okay, Sally pushes in the opposite direction. change the free body diagram. The force from Sally is still 5 newtons, but this time pointing in the negative direction. And now, when you find the net force acting on the shopping cart, we still have Bob in the positive direction, plus, now Sally, her 5 newtons are in the negative direction, so now you just would write it like this instead. 8 plus negative 5, or in other words, 8 minus 5. So 8 minus 5 is now only going to be 3 newtons. Okay, and as long as you draw me a picture of your free body diagram, which is basically going to be required on every problem anyways, and if it's not required, you should draw one anyways because they're super duper helpful. As long as you draw your picture, you don't have to specify exactly what direction your force is going in like you did before. Like you don't have to say 3 newtons east. As long as you drew the free body diagram, it's fine in this unit. Okay, so here, even though Bob and Sally are pushing in opposite directions, the cart ultimately is going to move in Bob's direction because he is using more force. He's pushing the cart with more force. So it's going to move in Bob's direction, except it's just going to be going a lot slower because he's not using, the shopping cart is not getting all 8 of his newtons. It's only getting 3 because Sally's working against him. Sometimes your force vectors will cancel each other out though, which is actually nice when that happens, makes the problem easier for you. So let's say now Bob pushes with 8 newtons and Sally pushes with 8 newtons in the opposite direction. The new net force on the shopping cart is 8 newtons from Bob, still in the positive direction, plus negative 8 newtons from Sally is going to give you 0 newtons. So what happens when there are 0 newtons of force acting on an object? When you have 0 force acting on an object, it means there is no change in the object's motion. So if it was moving already, the shopping cart, if it was moving already, and Bob and Sally canceled each other out, then the shopping cart would continue moving the same way it was before. If the shopping cart was still at rest before Bob and Sally started pushing, and they both started pushing with the same amount of force, the shopping cart would stay at rest. It wouldn't go anywhere. And that's pretty much common sense. Like, you guys get that, I'm pretty sure. Also, just to note though, if you have more than 2 forces, they can still cancel each other out. Obviously, you would know by the equation, even if you have more than 2 forces. But the key here is that you're only going to have a net force and your object is only going to move if you have unbalanced forces acting on your object. If you have a net force, and the only way you're going to get a net force is if your forces are unbalanced. So right now, our forces are balanced, and so therefore there is no change in the object's motion. If they were unbalanced like before, there would be a change in the object's motion. So keep that in mind, especially for like conceptual problems. Like if I ask you like a multiple choice question, for example, if the forces are balanced, no change in motion. If the forces are unbalanced, there is a change in the object's motion. Okay, and one more thing before I send you off to practice. we're still talking about free body diagrams and net force, but I'm going to give you a different example. Okay, let's say in this example, I'll just draw you the free body diagram. Okay, so in this problem, the free body diagram is going to be given to you, and let's say it looks like this. Okay, sticking with the 5 and 8 newtons today. They still want you to find the net force acting on this object, whatever it is. Just like in the projectile motion unit, you cannot add vectors together if they're not in the same plane, like the same x or y plane. Okay, so what that means for this problem is that to find the net force on this object, what we really have to do is find the resultant vector of these two forces. So the net force is your resultant force vector. And remember, to add your vectors, you draw them like, actually I'm going to do this one first, although it doesn't matter. You draw them tip to tail, so this one's my 5 newtons, and then I have my 8 newtons, and then here's your resultant. Your resultant equals your net force. So what does that mean? That means we're trying to find the hypotenuse of the triangle. So to find the net force, you have to do the Pythagorean theorem for this one. So net force or resultant vector squared equals 5 squared plus 8 squared is the Pythagorean theorem. Hypotenuse squared equals leg 1 squared plus leg 2 squared. And then you're going to take the square root of both sides to cancel out this squared. And your net force on this shopping cart or whatever it is now is going to be the square root of all this, which is 9.43. So if your forces are going in 2 different directions, some in the x direction and some in the y direction, you're gonna have to find the resultant vector using the Pythagorean theorem. You can't just add 8 and 5 in this situation like we did in the last example. Okay, and then lastly, what if your free body diagram looked like this instead? what would we have to do in this situation? Don't dread it too much, but it is trig again. Because, once again, this vector is in two different directions at once, the x direction and the y direction. So we have to break this into its x and y components using trig. So you would have to be given the angle here. So let's say the angle they give you is 30 degrees. Before you can find the net force, or the resultant vector, you have to break this one into x and y. The 5 newtons you don't have to break into x and y components because it's already only in one direction. It's only in the x direction. You only have to break the angled forces. Okay, so to break this one, I don't know what we're going to call it. Let's just say this is Bob, the force of Bob, and the force of Sally again. So we can say the force of Bob in the x direction equals 8, because that's our hypotenuse there, or the resultant there. Cosine of 30 degrees, because the x is adjacent to the 30 degrees. And the force of Bob in the y direction would be 8 sine of 30 degrees. And let's figure out what those are. Okay, so that would come out to 6.9 newtons in the x direction and 4 newtons in the y direction. So now that we have the components for this vector, and we don't need components for that vector, now we can go back to the original question, find the net force, or the resultant vector. And again, we still have things in the x direction and y direction, so we're going to have to do the Pythagorean theorem again. So it's the square root of everything in the x direction plus everything in the y direction. The only thing that you have to remember here is that you have two forces now in the x direction. You have the force of Bob in the x direction and the force of Sally in the x direction. And because they're both in the x direction, you can add those together here. So your x vector is actually, and if you want to write this out in multiple steps instead of doing it all at once, I actually recommend that. Maybe we'll do it over here. Force in the x direction total is going to be your 5 newtons in the direction we normally call positive. Actually, we could call this the sum of the x forces, just so we get used to using that symbol. The sum of the forces in the x direction equal 5, which is normally the positive direction, and then this x for Bob is actually, because this vector is going up and to the left, this one is going to be negative. So we should have probably added that here actually. Equals negative 6.9. Equals 5 plus negative 6.9, which is just 5 minus 6.9, which is going to give you negative 1.9 newtons in the x direction. And then the sum of all the forces in the y direction, there's only one force in the y direction, the force of Bob in the y direction, which is positive 4, because it's going upwards. And we don't have to add anything to it because that's the only one. So now we can go back here to find our resultant force vector of all of this combined. We're going to plug in negative 1.9 newtons in the x direction plus 4 newtons in the y direction, and figure out what that comes out to be. So your net force here, I got 4.43 newtons. So in problems like this, there are a lot of steps. However, I think that it will be more clear to you this unit, like which forces are going in what direction and what you're trying to solve for and everything like that, because there's not so many variables. We're pretty much only going to deal with force, mass, and acceleration in this unit. So there's really only going to be 3 variables that you have to worry about, and most of the time you're just going to be worrying about force, the one variable. So hopefully that is encouraging for you. So at this time, you should do some practice problems that I left for you on Newton's first law of motion. And once you're done with those, you can continue this video to see the rest of the notes, which are going to be on the second law of motion. And I think maybe we'll stop there with the second law of motion today. Okay, so Newton's second law of motion. Alright, so Newton's second law of motion answers the question, how does an object's motion change if there is a net force or an unbalanced external force acting on it? So assuming, like, when the net force is not 0, when there is some net force, how does that affect the object's motion? And this one is actually a math equation. I'm going to write it out in words for you first, though. So Newton's second law says that the acceleration of an object is directly proportional to the net force acting on it, and is inversely proportional to its mass. So let's write that. Okay, and also the direction of the acceleration is in the direction of the net force. Okay, so that's a lot of words, but what this really means is that your net force, or the sum of all your forces, equals mass times acceleration for your object. That equation, very important. I'm sure you've probably heard of it. Okay, so remember that acceleration is a change in velocity. So that means that you can change the speed of your object, or you can keep the speed of your object the same and change the direction that your object is going in, and that is also considered acceleration. So for example, if we go back to me swinging my lanyard around, okay, let's say I'm a robot and I'm really good at keeping this the same speed the entire time. The speed is not changing, it's going, I don't know, 2 meters per second the whole time. But this object at the end of my lanyard, the keys there, they are accelerating because they're changing direction. Going in a circle is changing direction. So there is an acceleration here, even though the speed might be the same. You can also change direction and change speed at the same time. It's also an option. Also, with that, keep in mind that if you have no acceleration, that means that you have a constant velocity, and your object could be at rest, your constant velocity could be 0, or like I was swinging my lanyard, your constant velocity could be, your object could be moving just at a constant rate. And both of those constitute as 0 acceleration. So same as last unit, just want to remind you. Okay. How do we use this equation in a word problem? Let's do an example. Okay, in this example, you have a 1 kilogram ball dropped out a window. And this ball experiences a constant 5 newtons of air drag. Draw the free body diagram for the ball. And we're going to calculate its acceleration. Okay, and for the sake of this problem, you do not know if you are on Earth or not. So that's why we have to calculate the acceleration. But first things first, draw a free body diagram for the ball. That's my ball. I know that it is 1 kilogram. So kilograms is a unit of mass, right? It's a lot like regular grams, but bigger. So 1 kilogram. So if you have room in your drawing, I like to write the mass of my object on the inside. I just think it's convenient, but you do it however you feel comfortable with that. 1 kilogram ball is dropped out a window and experiences a constant 5 newtons of air drag. So this object is in free fall. You learned a lot about free fall last unit. And we know that free fall is due to gravity. So I know that anytime I'm on a planet that has gravity, there's always going to be on my object the force of gravity pushing it downwards towards the ground, towards the center of the earth. So I'm going to label that Fg. That's usually how we denote the force of gravity, Fg, and it always points downwards. I also know that there's a constant 5 newtons of air drag. So if an object is falling, air drag is like air resistance, right? So the air preventing it from falling faster, the air resistance is going to be pointing up, right? Against the motion of your falling object. So the force of the air drag is your 5 newtons. What else do we know? Nothing, because we need to calculate the acceleration. So let's do calculate it. Okay, we'll just do this. We'll do it this way. Calculate its acceleration. So I'm going to just rewrite the equation. The net force, or the sum of the forces, equals mass times acceleration. So the first thing I have to do is make sure I have all my forces, right? In free fall, you don't have any forces in the x direction unless the problem tells you that you do. So this should be good. To find the net force, we have to be careful of 2 things, remember. Are all my force vectors in the same direction, x versus y? And are there any that are at an angle that I need to break into components? We got lucky on this one. There are no forces at an angle, and both of these forces are in the y direction. So that means to find the sum of the forces, we can just add them up normally. And I guess I should tell you what Fg is in the problem so that you can do that. Let's say the force of gravity is 2 newtons. Okay, add that in there. So now you can add this up. F air, usually up is positive, so we'll say that's a positive 5, plus Fg, downwards, so we're going to make it negative, equals the mass of our object, which is 1 kilogram, times acceleration. So just so you know, in these problems, the units that you want for F equals ma are newtons for force, kilograms for mass, and meters per second squared, same as before for acceleration. So if your mass is not in kilograms, you're going to want it in kilograms. Okay, anyways, now we can continue. 5 minus 2 is 3. 1 times A is A. So that's your answer. 3 meters per second squared is the acceleration due to gravity. Okay, so in this problem, the acceleration came out to be positive just because I made air resistance stronger than gravity on this planet. So that normally doesn't happen, but that's how it works on this made-up planet, apparently. Okay, and one more note about F equals ma. If this problem was on Earth, as most problems are going to be, so let's change this to you are on Earth. And let's say now, instead of air resistance, now, your ball that you drop out the window has a rope on it. So now, instead of 5 newtons of air drag, you have 5 newtons of tension force, or that's basically the force that you're holding up the ball with. And you still have the force of gravity, except this time I'm not going to tell you what it is because I did tell you that we are on Earth. So if you're on Earth, this changes a little bit because you can find Fg with minimal information, because the force of gravity, Fg, is equal to m times g on Earth, which is the acceleration due to gravity on Earth. So g is 9.8. So your force of gravity is always equal to negative 9.8 times the mass of your object. So if I tell you that you're on Earth, or actually, I guess you should assume that you're on Earth unless I tell you otherwise, you can solve for Fg using this equation. So you should write that down somewhere too. Force of gravity equals m times g, where g is negative 9.8. So now, even though I don't know this, I can still solve this problem because I know the mass. So the force of gravity here is going to be the mass, 1 kilogram, times the acceleration due to gravity on Earth, negative 9.8. It's going to give me 9.8 newtons. And then to find the acceleration, you can go back to this problem, and now your ball is not in free fall anymore. So the acceleration is not going to be negative 9.8 because it's only negative 9.8 if gravity is the only force acting on your object during free fall. This is not free fall because we have a rope that's holding up the ball. So that's going to change the acceleration of your object here. So you just fill out the equation as usual though. The sum of the two forces, they're still both in the y direction, so we can add them both together still. It's going to be 5 plus negative 9.8 equals the mass of the object, 1 kilogram, times acceleration, what I'm solving for. So this time, if we do 5 minus 9.8, you get negative 4.8 equals A. So negative 4.8 meters per second squared is your acceleration in this problem. So that means that even though you are pulling on the rope a little bit to hold up this ball, gravity is still beating you out. The force of gravity is stronger than the force that you are pulling up with. However, the object is accelerating towards the ground at a rate less than 9.8 because you are pulling up on the object a little bit and slowing down its acceleration towards the ground. Okay, so this is going to be important for you to know, as well as, of course, this one. Okay, and with that information, you can try the practice problems for Newton's second law.